Good morning. It's a pleasure and an honor to open this meeting. I'm very pleased to be here. I hope this will be an interesting workshop for everybody. I'm conscious that I can't make an overview of the entire subject of extragalactic jets in 30 minutes. So what I've decided to do is to pick a few key topics where I think we might be able to make some progress during this workshop, or in which recent progress has been made, and outline those to you in a few slides each. We know that jets are ubiquitous in the astrophysical world. Here are a few examples, the one in the bottom right-hand corner being somewhat of an artist's impression. We know that jets are found almost everywhere you have compact astronomical objects accreting or collapsing or spinning. We are going to concentrate on the extragalactic jets with a few nods in the direction of microquasars, but not consider the jets in, for example, regions of star formation, although we should bear in mind that those jets may have rather similar physical mechanisms. So these are the selected topics I'm going to talk about. They're ones that struck me. They're not exclusive. I hope we can have some discussion here. I won't dwell on that because they'll go past as we go through the talk. But first, to give you some basic numbers, just to make sure that we're all on the same page. The jet powers that we talk about for astrophysical jets in extragalactic sources are typically somewhere between 10 to the 41, depending where you put the boundary of what's a radio galaxy, and 10 to the 47 ergs per second. We know that relativistic bulk flow is fundamental, with typical bulk Lorentz factors somewhere in the range of 5 to 40 on sub-parsec scales. They're driven by supermassive black holes, by which we mean somewhere between 10 to the 6 and the record holder is somewhere around 2 by 10 to the 10 solar masses. The jets form in at least one or two cases on scales which are only a few tens of Schwarzschild radii, for example in M87. And they can persist, maintaining some sort of directional consistency for up to 10 to the 8 years. They don't all do that, of course. Some of them are very young. But we know from the very extended radio sources that they can be very persistent in direction. They radiate, and we identify them primarily by synchrotron and inverse Compton radiation from ultra-relativistic electrons. Therefore, they must contain relativistic electrons or positrons and magnetic field. They probably contain various other things as well, particularly thermal particles. How much of what they contain is a matter of debate. And they are capable of accelerating those electrons to extremely high Lorentz factors. I'm sure that that wasn't the right thing to do. Where's the pointer? I'm sure everybody is familiar with this characteristic double-humped, I'm going to have a problem with this, aren't I? Spectral energy distribution. This is the well-known TeV Markarian 501 BL-LAC object. Here's the synchrotron peak in the spectral energy distribution, and here is the corresponding inverse Compton peak at much higher energies. And that is characteristic of blazar spectra, and those mechanisms go together and will be present in essentially all of the objects that we'll talk about. So my first topic is simulations of jet formation. And this is something I hope we'll hear about, particularly from Sasha Chekhovskoy, fairly shortly. Currently, the most successful simulations, at least to my somewhat ignorant point of view, are those of magnetic arrested disk, MADS. What happens in those is basically that the accreting gas drags in a strong poloidal magnetic field. That field then disrupts the accretion, the axisymmetric accretion flow. And inside some characteristic radius, the gas basically accretes rather slowly in little blobs, or it streams in on a rather slow velocity. The interesting thing about this process is that it shows that the high spin case is really dominated by the Blanford-Znaeck process, It really is trying to extract the spin energy of the black hole rather than trying to be dominated by the disk. The same is not true at low spin. So it's a very promising way of generating generating jets that are not unlike what we think we see. But I would caution that the simulated disks are non-radiative and thick, and that's not clearly what we are always observing. I should say also that there are simulations which show jets from super Eddington flows rather than the rather tenuous accretion flows that are powering MADS. Those don't seem to be quite what we're looking at. The jets are slow. Well, 0.9 c isn't exactly hanging about, but they're not the speeds that we infer from VLBI. And they're radiatively driven. Whether that's relevant to the extragalactic case isn't particularly clear to me at the moment. Right, so this is a slide from Sasha's paper from 2011, illustrating what the MAD simulations do. On the left, the initial conditions, the density. The point here is that what you have is essentially an evacuated funnel here with a Poynting flux jet going up the center, a much slower wind around the outside. And the point of this plot is that the efficiency of the process in the sense of the power out divided by the m dot c squared in is bigger than 1. In other words, more is coming out of the in the jet than is going into the accretion flow. And that means that this is tapping the spin energy of the black hole, and it really is a Blandford-Znaiec process. This seems to me to be our baseline for comparison with observations at the moment, and hopefully we can talk a bit more about that at in the rest of the meeting. Now let me go on to something which Martin Hardcastle will discuss in the next talk, which is the relationship between the phenomenology of the accretion process and the output in jets. So traditionally, particularly optical and X-ray astronomers have classified active galaxies into two sorts, which in the radio galaxy context have come to be known as high excitation and low excitation. High excitation comes with a raft of phenomena which always go together. Bright permitted lines, broad if you see them from pole on, obscured from side on, an obscuring torus to do the blocking, the famous blue bump in the ultraviolet, strong X-ray emission. All of these are signatures of thermal emission from the accretion disk, and it's classic, essentially what Seifert found in 1943 is a classical active galactic nucleus. And if you talk to an optical astronomer, that's what they'll say an active galactic nucleus is. What they are physically are systems which are accreting at a substantial fraction of the Eddington rate. As Martin, I'm sure, will say, one of the suppositions is that they are primarily accreting cold gas from elsewhere in the galaxy. The other sort of accretion flow that we need to deal with, again in the radio galaxy context, are known as low excitation galaxies. And there it's actually very difficult to see any signature of the accretion flow at all compared with the jet. In fact, I was impressed at how little signature there actually was in the observations as opposed to the theory. These are radiatively inefficient accretion flows with a variety of acronyms for subtly different variants. They involve very massive galaxies and black holes, but very low accretion rates. And typically the observed luminosity from the accretion flow is a very small fraction of the Eddington rate, certainly less than 100th, and in some cases many powers of 10 below that. There is a suggestion that this is powered directly by accretion of the hot phase of the gas close to the nucleus. I'm slightly skeptical of this because all of the low excitation galaxies also have a rather complex multi-phase medium with cold molecular gas and warm molecular gas and possibly even neutral hydrogen. So I'm not sure that the accretion directly from the hot phase is exactly what's going on. But nevertheless, the accretion rate is much, much lower than it is in the high excitation objects. Just to emphasize how difficult it is to see the emission from the accretion disk in these objects compared with the jet, here's M87 from a nice recent paper by Almudena Prieto. And what you can see here is the nuclear spectrum in a couple of stages of activity. And I'm not doing very well here, am I? Let's go back a bit. How do I get this back into full screen? Sorry. Maybe I should do this with my glasses on. Thank you. Right. Yes, I will do this with my glasses on. It's a bit easier. So what we're seeing here is the nuclear spectrum of M87 with frequency here, and this is not a spectral energy distribution. This is a spectrum. And what's modeled here is a mixture of a jet component and a disk component. And the point I want to make is that the disk component is almost an optional extra here. If you do without it, particularly in this case, you can't usually tell the difference. And in fact, in M87, the models are actually only marginally better with an extra disk component added in. And that means the radiation from the accretion process itself is very faint. Okay, so in contrast to that, if you look at a high excitation case, this is the broadline radio galaxy 3 C120, which is a well-known superluminal. What you see is that this is X-ray observations from Suzaku. I'll come back later to discuss the fact that a dip in the X-ray emission precedes an ejection of a VLBI component from the core. That's been known for some years. Here, this isn't exactly the point. The point is the difference in the X-ray spectrum between this region here and the regions on either side. What happens during the dip? And this is from Anne Lofink's work. She's a student of Chris Reynolds. What seems to be happening is that there's a characteristic change in the spectrum of the disk just before the component is ejected. This is, I think, motivated by the situation in X-ray binaries. So we start off with a fully filled disk. Then the center of the disk between 20 and 40 gravitational radii disappears. Method of disappearance unknown. Shortly after that, stage 3, a radio component is ejected from the cleared disk, and then it refills again. And the reasoning behind this is fitting the ion line profiles and looking to see what the models give you for the inner radius of that. So there is some suggestion that the ejection of radio components does involve the disappearance of the inner disk, which is an interesting tie-in, particularly when you take that together with the fact that you also see jets in the low excitation systems. Final point on this topic is really to do with black hole spin. The MAD models work best, by far best, at maximal spin, A close to 1. It's therefore somewhat a surprise that when you actually try and measure the spin of the black hole using the relativistically broadened ion line, there isn't really at the moment very much obvious difference between radio quiet and radio loud objects. Now this is based on a sample of a total of 2 radio loud objects, which is not particularly useful, but there they are, 3C120, which we just looked at, and 1921. But nevertheless, it is rather strange that there isn't an obvious clustering of radio loud objects at the A equals 1 line, and more importantly, I suppose, that the radio quiet objects are actually also really rather high spin. So there's something to be looked into here.
Most of these high excitation galaxies?
They're all high excitation by definition, otherwise you wouldn't see the X-rays. Yeah. No, you can't do this with a low excitation galaxy because you can't see an ion line. So these are the questions I have for later on accretion mode. So why are the jets in high excitation and low excitation galaxies so similar despite the gross differences in the accretion disk? There is an observed difference which we understand, we think, which is that the inverse Compton scattering is different, and that's because the incident photon field on the jet is much higher in the high excitation systems. But otherwise, they're rather similar. Why is there a correlation between accretion disk luminosity and jet power if there isn't, if both sorts of galaxy can produce jets? Is this something to do with the strength of the magnetic field that's being brought in? Is the disappearance of a thin disk at small radii a necessary condition for jet formation, and if so, why? And is there, in fact, why is there no obvious relationship between efficient jet production and measures of black hole spin? And just a small rant at the bottom of the page, if you'll indulge me, please can we stop using the terms radio loud and radio quiet quasar? Basically what you're doing here is you're dividing an observed radio flux by an observed flux in the optical, which is an unholy mixture of X-ray emission from the accretion disk, stars, and emission from the jet itself. This as a ratio means nothing. I think we should start using the jet luminosity and the accretion disk luminosity separately and not ratioing them. End rant, return. So my next topic is where do the jets light up? We observe them a whole range of wavelengths, but where do they actually turn on? Where does the radiation come from? The answer to that is now rather precisely known in the radio for nearby radio galaxies. So here are two examples. One is M87 and the other is 3C270. I haven't made a spelling mistake. These people have almost the same names, but not quite. So the technique here is the core shift, which we'll come back to. We're observing here in the radio, and what we're observing is the position of the tau equals 1 surface for synchrotron self-absorption. As you increase the frequency, that gets closer and closer to the apex of the jet. And where that asymptotes is essentially where the jet turns on, where you first start getting some emissivity to be self-absorbed. And indeed, what you see is this asymptotic profile, which for M87 ends up very close to where we think the black hole is. This is a nice example because it's got jets on both sides, if you measure the position of the apparent core, it essentially coincides on the two sides of the jet to very high accuracy. So what that means is the jet turns on extremely close to the black hole within a few tens of Schwarzschild radii in the M87 case. Or not. So this is a different way of looking at things. This is back to a situation which was motivated by 3C120 from Alan Marsh's work a long time ago, the same observations as I was showing you earlier. What you see is a dip in the X-rays, and then somewhat later a component is ejected. Alan Marsh's point of view is that you see that component only when it reaches a shock here, a standing conical shock. That's the radio core, not something down close to the black hole. That depends on the assumption that the component, the delay is actually the light travel time of the component moving down the jet, which it might not be. But nevertheless, this is a high excitation object. Maybe, if this argument is correct, the standoff distance of where we first see the jet from the black hole is much, much larger than it is in systems like M87. So I think we need to understand that and see whether there's a real difference between these objects or whether we're misinterpreting something. Next topic, magnetic structure and magnetic field strength and geometry. The magnetic field is clearly crucial to the collimation and evolution of the jet. And so what constraints do we actually have on the field itself? How is, what's its vector structure? Is it ordered or disordered? What's its strength? And we have sort of bits of information on different scales which are not quite the same, but which interlock to give some sort of picture. On kiloparsec scales, we think we know that the field evolves from primarily poloidal to primarily toroidal on scales of a few kiloparsecs. That's not a globally ordered helix, because otherwise you would see asymmetries in the radio structure that you don't see. So probably what it is an ordered toroidal component and a poloidal component with many reversals. The field strengths are guessed at from equipartition. There isn't a good inverse Compton constraint, but are probably not too far from the truth. I'll come back to FR2 jets a little bit later. On parsec scales, the same core shift method that we were looking at earlier gives you the magnetic field strength at round about a parsec, and with additional assumption also the magnetic flux. So that, and I'll show you a picture of that in a second. The field geometry is debated. There are those who would like a helical magnetic field in the sense of significant poloidal and toroidal components. My own preference is for a toroidal field with more of a disordered poloidal component, as on kiloparsec scales, and there are those who would want to go for a field that's disordered and anisotropic, which also gives high polarization. That debate is still ongoing, and I think we can take that forward at this meeting, particularly after Denise's talk. Here's the magnetic flux from core shift, a subject populated by people with names beginning with Z for some reason. And the point here is that this is plotted against the square root of the accretion-disk luminosity, and this is the magnetic flux. And this is the reason for this line is that this is roughly the prediction from the MAD models, although there are some differences of opinion on the precise jet geometry, which leads to different answers for the value of the magnetic field strength, which is what's different between those two papers. And this is what we think is going on kiloparsec scales. So this is plots of the fractional poloidal component here, the fractional toroidal component there, in a sample of 10 low-power radio galaxies evolving on kiloparsec scales. And as you can see, we're going from primarily longitudinal on the scales down here to primarily toroidal out there as we evolve. I won't go into how we get the 3D field structure. Come and ask me if you're interested. Okay, next topic is, do jets really accelerate from beta equals 0 when they start to beta equals 1 and then back down again, or are we getting misled? This is a very nice plot of data for M87 from proper motions, starting out close to the core, down here, with some rather slow speeds in general, meant for people with smaller fingers than me. And then round about here, there's a apparent acceleration. So these are apparent velocities up the side here, and so superluminal up here, a maximum of about 6c measured, and then back down again as the jet goes further out at the famous not A. So one way of looking at this is a real bulk acceleration. So the jet is going at beta equals 0 for a bit, and then around about 100 milliarc seconds from the core suddenly accelerates. I'm not sure that that's the right way of looking at it, because if you look at the fine scale structure of what's happening on the few milliarc second scale and use a wavelet analysis, which Mertens and Lobanov have done, then you discover there are actually superluminal motions also in the base region of the M87 jet. The other thing is that the jet to counterjet ratio is very large, which suggests that the flow speed is significant. So my guess here is that we are seeing some acceleration, but it's not from beta equals 0 down here. But I think still the interpretation of the proper motions and the jet to counterjet ratio is not certain, and we need to look at that. That slide didn't seem to come out too well. Never mind. Let's concentrate on the bottom panel, which makes the point. This is some evidence of what transverse gradients in velocity are doing on parsec scales, or was, before somebody put a black box on top of it. What we think is happening is that the flow at the edges of the jet is much slower than the flow on axis on these scales. And there are various pieces of evidence which suggest this. And one of the most obvious is limb brightening of the jet. So the supposition is what we see here is that the central flow is beamed away from us and is therefore suppressed. What we see primarily is the flow from the edges of the jet. And the bottom example, which seems to have survived, is Cygnus A, some from very recent work from Bier-Bacardi in Bonn. So here's the nucleus of Cygnus A on parsec scales. You can see the limb-brightened structure in the approaching jet. And if you make some plausible assumptions about the angle to the line of sight, you can look at what the velocity of the components that are moving out in this jet are doing. And what you can see here, this is a component in the center of the jet, which is accelerating up to beta equals 0.9 something. This is a component, a set of components, I should say, in the shear layer of the jet, what we presume is the shear layer of the jet, which are going significantly slower. They're both, I'm not going to say accelerating because these are different components. They're going at faster speeds the further you get from the nucleus, but they are going significantly faster on axis. So that model appears to be viable on parsec scales. We think it's also viable on kiloparsec scales in the opposite sense that we have jets which are decelerating, and this is work that we've done for a long time on decelerating low power jets. And what you can see here is a plot of the velocity in units of c. And in all of these cases, what we can see is that the jets are decelerating quite rapidly. And in a number of cases, they also develop a transverse velocity gradient in the same sense as we see on parsec scales. The outside is going slower than the middle. And we think this is a result of boundary layer entrainment as the jets pick up some of the external medium and slow down. So some questions about velocities. Is the bulk acceleration real? What are we measuring with the proper motions? We've had this problem ever since superluminal motion was discovered. What does it actually mean? Are we seeing components moving with the flow? Are we seeing moving shocks? Are we seeing something else? And also, how fast are the powerful jets on kiloparsec scales? We have quite good constraints on the low power jets now, but we don't really know too much about how the high power jets are behaving. However, we are trying, and this is work in progress. This is the giant radio galaxy NGC 6251, which is very much a transition case between low and high power. The very famous one-sided jet here. There is actually a counterjet, which you can't see very easily. This is very new VLA data at 5 gigahertz, and what we're trying to do is the same sort of analysis as we've done on the low power sources, to deduce the velocity field in the jet. The early indications are indeed that this jet stays fast, and that the spine of the jet is significantly faster than in the low power cases, maybe up to a gamma of about 5. And you can see already, if you look at the original plate, as they used to say, that the main jet is significantly more center brightened than the counterjet. Counterjet is actually somewhat limb brightened, and that's exactly the signature you expect if you see a fast flow in the center of the jet here, and it's beamed away from you in the center of the counterjet. I don't want to get too specific about that because the data reduction is somewhat nightmarish, but yeah.
Which source is that?
NGC 6251. Okay, in honor of Bernie, a few slides on the Fanneroff-Reilly division. So here are some Fanneroff-Reilly class 1s on the left and Fanneroff-Reilly class 2 on the right. As I'm sure everybody will remember, the distinction is that class 1 sources are bright in the middle and class 2 sources are bright at the outside edges. To put some more physics on that, the jets are, these are the characteristic bright jets in the center of FR1s, and the hotspots, which are the termination points of the jets in FR2s. So one thing that's been quite an interesting fact, or thought to be a fact, in understanding how this division works is how it depends on environment. And so in the mid-90s, Michael Ledlow and Fraser Owen came up with this diagram. Fenneroff and Riley, of course, pointed out that FR1 sources are low power and FR2 sources are high power, which to a first approximation is certainly still the case. But Ledlow and Owen pointed out that if you plotted this in a diagram which has optical absolute magnitude along the axis here, so that bright galaxies are on the right and radio power up there, you get a diagonal line dividing it. So this was prima facie evidence that the FR division depends on environment as well as radio power. The situation, unfortunately, has got rather more complicated recently. So this is results from a very large sample of overlapping SDSS, FIRST and NVSS optical radio cross comparisons. And here the blue points are the FR2s and the red points are the FR1s. As you can see, it's not nearly as sharp a division as the first diagram suggests. And I think the reason for this is that in the Ledlow and Owen case, objects were being picked from quite far apart on the luminosity function, and so that's exaggerating the difference, which is still there in the more recent data, but not nearly in such an extreme manner. Another small rant at this point, just to say, and this is important for feedback, which is that the FR1 sources are not just objects that tail off into nothing. They very often form lobes in the same way that the FR2 sources do. Here's a nice example, clearly an FR1 source within the meaning of the act, but with perfectly well-defined lobes. No hotspots, but the characteristic spectral index pattern, which also you see in FR2 sources, flat spectrum at the edge, steeper spectrum towards the center. So it's clear what's happening here. Material's going up the jet and then back into back to form the lobes. And the point I want to make here is that this is very common, firstly in FR1 samples, and it's important if you want to calculate the effects of these sources on the environment. You shouldn't assume that they're tailed sources going off into the middle of nowhere. They interact differently with the intergalactic medium, and they interact in the same way as the FR2 sources to a first approximation. Okay, so what do we know now that Burney didn't know in 1974? I've put what I think we know now in bold. Fairly soon after the Fenneroff-Riley division was discovered, a number of people came up with the ideas that jets are Kelvin-Helmholtz unstable. They might entrain material and decelerate. They might become turbulent. They adiabatically compressed, and so the brightness would stay high. That's part of the story, but not all of it. We've discovered since then that the FR1 jets also have to accelerate particles effectively, otherwise they wouldn't emit synchrotron X-rays. And we now, I think, have a consistent picture of the way that they slow down. We understand what their power is, how their speed evolves with distance, and how their density evolves. And so it's not just adiabatic compression, it's also dissipation of energy, which leads to high energy emission. The FR2 jets we now know are relativistic, but we don't know how relativistic. We know that they don't decelerate significantly on kiloparsec scales, but we may have the same situation as we have on parsec scales, a spine shear layer structure with quite a fast spine, and that we need to find out. Okay, well, one argument is that if you look at the asymmetry in the depolarization, which is external, then the nearer jet, which is the brighter one, shows less depolarization, so it has to be on the near side. Also, it correlates with the fractional core luminosity. The VLBI jet and the main jet are always on the same side. So there's a consistent picture that says they're relativistic. It doesn't say, it doesn't say what the velocity is, but it has to be significant. I mean, if you look at the the ratios of jet sidedness, which Martin has done, for example. The naive answer that you get is, he wasn't naive, I don't mean that, but if you assume a single velocity, you get about 0.6 c, but if the center of the jet is going much faster, then you don't see that. So. The kiloparsec scale jet is always brighter on the side of the VLBI jet. That's correct. Which is said to be relative. This is the whole argument that we Yes, exactly. You have to have continuity. You can't have relativistic stuff on one scale and not on the other scale, exactly. One thing that would be very interesting to come back to, and Gopal Krishna is one of the people who's contributed this, so it might be interesting for him to come back to, is what's the quantitative basis in the Farrow-Riley classification? There were two attempts that I'm aware of to fit the Owen-Ledlow diagram in the early days. One from Jeff Bicknell, whose argument basically be summarized as saying that a jet can only remain collimated and slow down if its power is less than something. In other words, if it entrades too much, it blows apart, so it's not identified as a jet anymore. And that's the cause of the Farrow-Riley dichotomy. The snag with that argument is that that doesn't actually tell you what the entrainment rate is a priori. So it only says if it entrains, then this condition holds. Gopal Krishna and Wheater a little bit later suggested that the criterion should be that the bow shock velocity becomes transonic and say that the lobe collapses. I'm not sure I think that fits with the existence of lobed FR1 sources, because there the lobe clearly hasn't collapsed, and the phenomenology is otherwise rather similar for FR1 jets. But I think this is a subject that bears going back to now we have much better data. Another small rant here, just to make absolutely sure that people understand that the Farrow-Riley classification and the distinction between high and low accretion rate radio galaxies is not a one-to-one mapping. It might look like it, and the reason it might look like it is that if you look at the luminosity functions, then what you see is that nearby the space density of radio galaxies is dominated by the low excitation Farrow-Riley class 1. And so you might think, well, low excitation equals Farrow-Riley class 1, and similarly at the high luminosity end, that everything is dominated by high excitation FR2s, which statistically speaking is true, but that doesn't mean that the objects are actually the same. And here are a couple of examples. Catherine has shown a number of others. This is a perfectly well behaved FR1 radio galaxy with an obvious broad line spectrum, H alpha and H beta. This is a perfectly well behaved Farrow-Riley class 2 with a spectrum of a passively evolving elliptical galaxy. So it isn't a one-to-one mapping, and models that are based on it being a one-to-one mapping, I think, are not really tenable. Final topic, before I go on to observations, is the impact of jets on their surroundings, which is important and in some ways more important than we thought a few decades ago. The reason primarily being that I think our estimates of jet power have been inching up during that period. Primarily, the reason is that we now have much better X-ray data, so we know the external pressures of these objects much better, and those are substantially higher in some cases, particularly in the FR1 cases, than the synchrotron minimum, which we were using before. Given that we use the PDV work done to expand the lobe as a measure of the jet's energetic impact on the external medium, that has caused our power estimates to go up, and therefore our estimates of what jets actually do to their surrounding medium, to star formation, to the evolution of the galaxy, that has now all become significantly more important. Here are two examples of radio galaxies interacting with the surrounding X-ray gas. This is M84, which is a titchy little thing in the Virgo cluster, So everything here is happening on 10 kiloparsecs galactic scale. The radio source is clearly pushing the X-ray gas out of the way. Here's a giant example, Hydra A, which is a cluster center galaxy doing precisely the same thing on a much larger and more energetic scale. And I think Ramanujan will talk about we'll talk about that, the diagram on the right in a bit more detail. This is a plot of the radioluminosity against the power inferred on the PDV work done to inflate the cavity, showing a quite reasonable correlation over some orders of magnitude. A lot of scatter, but nevertheless, it's a good way of at least a first order of estimating the jet power. But it's not just the X-ray gas that gets pushed out of the way. And an area which is becoming significantly more important these days is looking at what happens to the molecular gas, and not just the cold molecular gas, which one I'm showing here, but also warm molecular gas that you would see, for example, with Spitzer, which is surprisingly prevalent in some of these objects. So just one example of new results from ALMA. This is a compact steep spectrum source, IC5063, in the south, and what's plotted here is the 230 gigahertz continuum from ALMA as contours, and the integrated CO2 to 1 emission as color. And what's on the right is a position velocity plot showing that the width of the velocities in the central region here, which overlaps with the central radio component, is extremely large. And what that means is that there is an outflow which is being driven by the expansion of the radio lobe. Not so much driven by the jet, but driven by the expansion of the small lobe around the source. Here's an example from what Alan Bridle and I have been doing about impact of jets on the surroundings, or impact of the surrounding on the jets, whichever you prefer. What we can do now, once we have the velocity fields that I showed you earlier, is to use the conservation of energy, momentum, and mass to infer how the jets are slowing down. And the point I'd like to make here is that the jets are changing from dominated, so this is a quantity you probably can't read. This is rho c squared over the enthalpy density. So it's a measure of how how dominated by the entrained material the jets actually are. When they get larger, it means there's relatively more thermal matter that's been entrained. So that's increasing down the jet, and so we have 4 cases which fit quite well here now. They're all transonic deceleration, so they're all round about Mach 1.5, Mach 1. They're all entraining significant amounts. The interesting thing, which I haven't quite got my head around yet, is that the 2 cases here are the lobed FR1s, if you'll remember, and the 2 cases down here are the tailed FR1s, which are actually showing relatively less entrainment as you go further out, which is actually the opposite of what I would have expected. But nevertheless, you can do quite a lot with this type of argument once you know the X-ray pressures and densities. So just a quick summary of jets in a multi-phase medium. We need to remember that there isn't just hot gas, there's cold molecular gas, there's warm molecular gas, there's H1, there's all sorts of stuff in there. The jets will displace the hot gas, they'll shock it sometimes, usually with rather low Mach numbers, but occasionally up to 10 or so. The interesting thing, which I think has been emerging rather from very recent observations, is that in many cases the entrained thermal material may dominate the pressure of radio lobes, and therefore we need to think about how the gas that's entrained gets heated to an extent that you can't see it in the X-rays, but it may be the dominant pressure term, and this is an important thing to work out. The cold molecular gas, we're getting increasingly better observations now. ALMA's come online, it can dominate the mass outflow. What you see in the molecular gas is probably cooling behind the shock around the radio lobe. But the energy budget is surprisingly efficient. I mean, it's probably almost up to 10% of the jet power. So there's a lot going on here that's being driven by the jet. And there are starting to be simulations of this type of process, and I'll just highlight this one, which is by Wagner and Bicknell a few years ago, of a jet propagating through a clumpy intergalactic medium rather than a nice smooth one, purely hot gas that we were discussing earlier. Okay, I will end by just giving a very brief observational prospectus. There's a lot going on at the moment, and will be a lot going on which is relevant to jet physics. Here are a few highlights. Hopefully within the next few years we'll get the Cherenkov telescope array, which will give us much more sensitivity and somewhat more resolution for TV gamma rays. We're already in the position of being able to use ALMA to look at molecular inflows and outflows. JWST and ASTRO-H will give us those capabilities in the infrared and the X-ray. Hopefully at some time in the not too distant future we'll have at least the first phase of the SKA, which will augment the capabilities we already now have with the expanded VLA. Maybe if plans in the US go ahead, we'll have the new generation VLA a little bit later. The subject of does the X-ray emission come from synchrotron or inverse Compton will benefit a lot from having an X-ray polar emitter on a satellite. There are many proposals to do that, one of which will eventually fly. But I'd like to end up with what I think is, for me, the most exciting near-term prospect, which is doing millimeter VLBI with phased ALMA. And if all goes well, we hope to be able to offer this from the beginning of cycle 4, which is October of next year. So there's ALMA on the Chajnantor Plateau. What you do is you phase up the signals from 50 or possibly more of the antennas. This is a standard technique in VLBI now. It gives you the equivalent of an 85-meter single dish if you do it perfectly, and it's on a very good site. And this is what makes the difference between being able to do millimeter VLBI with a fringe spacing of around about 20 microarc seconds and being able just to detect the odd fringe from time to time. And so hopefully you can do real imaging with an array of telescopes which viewed from M87 looks something like this. This is a simulation of what you should see. And this final graph connects back into the research program here at ICTS because this is real relativistic astrophysics. This is attempting to see the shadow of the black hole event horizon against the background source that is the M87 jet. And hopefully this will be something that will be doable within the next year or two. And I'll stop there, thank you.
I have a couple of questions.
Sorry, where are you?
Yeah. So first one is about the limb brightening figure what you showed.
Yeah.
The limb brightening structure. So you are trying to explain by the differential Doppler boosting, am I right?
That is, yes. So I mean, I should say, if you see a two-sided jet, you can resolve the degeneracy, because obviously limb brightening can be enhanced emissivity in the rest frame, or it can be a beaming effect. And you can't just sort of look at it and say it's definitely a beaming effect. However, if you see a jet which is intrinsically symmetrical, and you can compare the two sides, you can figure out which of those is, because obviously the emissivity variation is symmetrical and the beaming is not.
Right. The question is that, the point is, if it is a limb brightening is due to differential Doppler boosting, then you don't find the difference in the spectral indices in the limb and the core spine. The indices should be same. The radio indices should be same at the spine as well as the sheath. So there's an alternately, there's a shear acceleration.
Yes, I don't think, I take your point. I mean, and we've actually tried to look for transverse spectral gradients, and we have in fact found them in one object, one of the FR1 objects.
If you find an index change, then it cannot be due, there can be differential boosting, but it cannot be fully attributed to the boosting.
Yes.
There's one question.
Yes, I agree with you. And I mean, in the case that we actually have, which we published a couple of years ago, we did not favor differential Doppler boosting as the cause of this. We think it's an effect which is due to the difference in velocity, and it could very well be that shear acceleration. So I agree with you on that.
Yeah. So one more. Can I have one more question? Yeah. The other one is that you said about the acceleration and deceleration in the parsec scale. Am I right? The apparent acceleration and deceleration in the patterns, right?
The acceleration is on parsec scales. The deceleration is on kiloparsec scales.
I have one question is, can this acceleration due to be the bending of the jet? See, as it bends, the viewing angle change. So apparently I can see...
Only in individual cases.
Correct.
And in M87, it's extremely implausible because the jet on the plane of the sky is dead straight.
Okay.
So I don't think so.
Okay. Thank you.
Robert, just to pick up this question of beaming effects as an explanation for the edge brightening. Now, maybe I'm looking at this wrong, but if that were what was going on, would you not expect to find some sources where the central part was actually better aligned and you got center brightened?
Yes.
So is that an argument for against that as a kind of a general explanation for the edge brightening?
No, I don't think so, because I think the cases where the limb brightening is most extreme, like M87, are not actually that well aligned. I mean, the cases where you see the center brightened in the approaching jet are the cases in which the alignment is very good. I mean, let me just go back, if I may, to the...
Okay, I mean, could there not be sources where you actually... Could there be sources where you actually did have a slower material around the edge, but they're not edge brightened? I mean, they're not edge brightened.
I mean, this is what I was trying to say in answer to the previous question, that you can have intrinsic emissivity variations and you can have relativistic ones, and you need to figure out which of those is operative. Either may be operative in a particular case. The way that you can tell them apart if you have a system that's symmetrical is to look at the differences between the counterjet and the main jet. If in any case, if you have a sufficiently well-aligned object, then in the approaching jet, you should see a center-brightened structure if it's relativistic. Arguably in some of the most extreme blazars, that's what we're seeing. But the argument is being made, for example, for the TV blazars, such as Makarian 501, that you need this sort of structure anyway, because what you need to do is essentially to have a different beaming factor for the TV gamma ray emitting region and for the radio, because in the radio you see these rather low proper motions. And the picture there, I'm not sure whether it's right, but the picture that's been promoted is the outer layer of the jet is moving more slowly. That's what you see primarily in the radio, and that fits with it being a limb brightened structure. The trouble is you can't see the counterjet in Markarian 501, so you can't check that possibility.
And could you possibly just briefly comment on, you said that the Owen-Ledlow plot, the Ledlow-Owen plot, showed you that there had to be environmental effects affecting the difference between the FR1 and FR2. And I didn't understand that, because it would seem to me that both the radio power and the optical magnitude were maybe telling you something about the central engine. This has been a debate which has been going on for some time. So yes, I agree that's one possibility. And there have been attempts to interpret this diagram as something which is tied to the mass of the central black hole, because that's obviously correlated with the variable on the x-axis. And so there have been suggestions that it was the mass of the central black hole that was responsible. The alternative explanation, which was behind Jeff Bicknell's 1995 paper, is that the other thing that's correlated with it is the central gas profile. So what the jet is propagating through is very different for the faint galaxies at the left-hand side and the cluster center galaxies on the right-hand side. So it's a messy problem. I mean, I agree it doesn't have to be environmental, but environmental effects are there. Yeah, I was just surprised that you said that you would draw that from this plot.
actually
It's
sounds
not
like
a
mostly
unique
from other-
inference, no. I mean, and that's why it's been, it's been contentious over the last few years. I mean, my feeling is that it's probably not driven by the black hole mass, but let's talk about that later.
Yeah, so now I am not sure how many cases of FR1 jets having lobes are known, but could there be transition objects in which the lobes that you are seeing formed during a stage when the Mach disk was still strong and there was a backflow, and now the Mach disk has weakened because of it's becoming subsonic?
Yes. A couple of points. Your first point about the statistics. The statistic I have in my head is that 50% of the B2 sample of nearby radio galaxies are lobed FR1s, 50% of the FR1s. So it's not a trivial number. It's sample dependent, and I think Lakshmi Saripalli came up with a somewhat lower number. So I don't know whether there's a single number that one could quote, but they're not rare. So your question about whether there could have been a Mach disk in the past, yes, there could have been a Mach disk in the past. However, I mean, we have found two examples of sources where we think backflow is occurring without a hotspot being present. So these are lobed FR1s, and what we see is, what we think maybe is a backflow around the central jet going back towards the nucleus. There's a high pressure region at the leading edge, but it's not formed a hotspot, so it's probably not supersonic. It's fast, but it's not supersonic.
Okay, let's thank Robert very much once more for